computer. Thank you. Okay, so what we have seen in the last lecture was that, you know, when we have an electromagnetic wave, the electromagnetic waves are essentially the E field and the B field are transversal to the direction of propagation. Okay, so if the you know, the direction of propagation is something like this, like the S pointing here, E and B are in a plane perpendicular to that. Okay, so that is our main result. And the next one is that there are two directions of what we call polarization. You can have a polarization in the X and the Y direction, considering that the wave is traveling in the X direction. This is in general, you know, that you can always rotate the axis of the system to align yourself with the direction of propagation, and then you will have two independent directions over which the electromagnetic field can be defined. Okay, and E and B are perpendicular to each other in vacuum. It's very important that happens in vacuum, and so they can at least transport information. Okay, so but they do something else. They not only transport information, they transport energy. So this is not only energy but also momentum. Okay, so this is going to be the argument during this lecture. So what we have learned in our previous courses is that the energy density of a field can be defined as this is energy density. This is joules per cubic meter in MKS systems. It's simply defined like half epsilon naught E squared plus B squared over 2 mu naught. This is essentially the energy density of any field configuration, any free region of space where only E and B exist. Okay, this is supposed to be vacuum because we're saying it's E naught and mu naught. Okay, epsilon naught and mu naught. So that means that it's empty space. Okay, so it's not inside a material. If we were inside the material, we have to change this by mu and epsilon and you know, take appropriate considerations about, you know, if things are linear and whatnot with respect to the size of the fields. But that's a completely different story. We have to change it depending on the materials that we are. Okay. So for a particular electromagnetic wave, what we have is that E naught, we can replace this thing. We have to remember what we did last class. We know that the maximum intensity of the field, the B max, is equal to the E max divided by C. So if I replace that in here and do all this little algebra that has been shown here, no, nothing happens. We can get to epsilon naught dot times E squared. So this is the energy density for an electromagnetic wave. So that should be the case in general. Okay, but let's consider for a moment a wavefront that is described by this plane A. Over this region behind the plane A, there's this electromagnetic field that is trying to flow, and then we take a picture of it and it looks like that. And then we take a picture and this region here is empty. And we let the field evolve and it will displace in this direction, and we will have fields in this region here of space. Okay. So the energy density of the field in here can be written in this way, particularly in this way, because it's an electromagnetic wave. Okay. So before we didn't have any field in here, and then after dt, we will have this whole volume full of energy. So we would like to consider those two planes, and actually the total energy in this volume here, okay, the total energy of this volume here is simply, what is that? It's the volume, which is CDT times the area A, that's the volume, multiplied by the energy density, which is exactly this amount. Okay, so that will be the total energy in this volume. Okay, let's go to the next view graph. How we do this? Okay, so the volume that now contains this this electromagnetic energy is ACDT, which is, you know, the differential volume. So the total energy contained in this new volume is the energy density times the volume. So this is the energy density, and that's the volume. And so what is the interesting part of writing it like this is that this energy has passed through the area A in a time dt. Okay, so whatever energy is now filling this volume space went through that area. On what time? On the time dt. So we can define the energy flow per unit area per unit time, and we define it as this letter S in vacuum, which is well, the total energy that we have here divided by the area and the time. So that would be the energy that has passed per unit area, well said, per unit time. And that is simply this expression here. So, and this also should be familiar. Essentially, the flux of the energy is the energy density times the velocity at which the this density travels in space. Okay, so that's the flux. So energy density times velocity. Okay, so the idea then is that you know, any electromagnetic wave contains energy, and it can be expressed like that. I could also write this up in terms of the B field, but it's usually done in terms of the E field because it's the stronger field. Okay, but the size of the B field and the E field are exactly the same. And actually, for electromagnetic waves, how can I go back here? This, for an electromagnetic wave, this size, this energy is equal to this energy, because otherwise you cannot get, you know, it's a half E0 times E squared, and this must be a half E0 times E squared to get the same energy. So the energy contained in the E field and the energy contained in the B field are the same. Okay, so that's why you get this expression at the end. Okay, yeah. So this is the energy flux. The energy flux is the energy density times the velocity. But, you know, we can actually improve this, trying to include the direction of the field. So, you know, this S value that we have there can also be written in the following way. This is 1 over E naught mu naught is the speed of light. Okay, so I'm just rewriting whatever I had in the previous transparency, and taking that into account, I now can write the E field here, one of the E fields in terms of the B fields. So this would be the S value would be E times B divided by mu naught. Okay, and that is it's a very relevant quantity. This quantity S in general is measured as you know, it's energy divided by unit area by unit time. So it's essentially joule divided by time divided by area. So it's a flux divided in it's a power flux. It's watts per meter square. That actually, this is the way you actually label the energy contained in an electromagnetic wave. Okay, so in addition to this quantity S, we can also introduce a vector quantity defined in this way. This is a reason why I wrote it this way. So starting from S and got this way, because I can write it as, since E and B in a electromagnetic wave are perpendicular to each other, E cross B is essentially EB, and mu naught, perfect. So this S quantity is equal to S times K. What is K? K is the direction in which the field is propagating. So E cross B, as I mentioned before, is the direction in which the field is propagating. So now S not only has the right value in terms of, if we define it as a vector, as E cross B divided over mu naught, it has the right value for the the power over the rate of change of the energy as a function of time and surface per unit area, but also the direction in which that happens. So not only the magnitude of the energy flow, it's contained in the but also the direction. Yeah. So let's say we have an enclosed volume where you have an E field and B field going out like that, isn't it? So you have, and this is the direction of the wave. So you have an E and B perpendicular. Let's say you have a source of electromagnetic waves inside, and you want to find out what is the power that is being delivered by that. The only thing that you have to do is actually integrate this vector S over the whole surface. Okay, so essentially calculate the flux. If you calculate the flux out of the surface, you can determine the total power delivered. Now it's not power per unit area. Now it's the total power delivered. Okay, this is also relevant for in communication. It's an interesting aspect to consider. Yeah. Now for sinusoidal or exponential waves, this S is in general a function of time and position. Okay, so S as a function of X and T would be this expression here, and now what I would do is bring my electromagnetic wave. X is the direction of propagation. That's what I'm saying. So, and then Y is the direction in which the E field is polarized. Okay, so I'm just simply rewriting this term as a function of this traveling wave, cosine of kx minus omega t. The same is true for the B field, which also have the same amplitude. There's no phase difference between both because they are linked by Maxwell's equations. And if we do that square, we get this beautiful expression. And we can then make the equivalent of the cosine square. We can write it like this. And we find that Sx, the component of S in the direction of X, which is the total modulus of the S vector, it's actually equal to the product of these two things divided by 2 mu naught, Emax, the maximum value of the electromagnetic wave in the wave, that Emax, and this Bmax over here. And the singular aspect is that this thing is Sx is always greater than 0. Okay? This term over here, when the numbers are right or the time is right, could actually be -1. But that will be, if this is -1, this whole Sx will be at that instant will be 0. But otherwise, it's always positive. So it's a cosine. It's a cosine square essentially. What is we are looking at, and so it has. If we average it over time, this quantity, the only thing that counts is the first contribution here. Emax Bmax over 2 mu naught. Okay. And so that is an important thing to remember. The average value of this S This S vector is called the pointing vector. I didn't write it down. I should have done it. Okay. And the average value of that is what is called the intensity of an electromagnetic wave. So the intensity is measured in watt per meter square. And when somebody quotes it, it's not the maximum value, it's not the minimum value, it's just the average value. And the average value is exactly equal to the maximum value divided by 2 mu naught. So essentially what we're doing here is taking the average over a complete period of the electromagnetic wave, okay? Perfect. So we have an expression now that there's energy contained in an electromagnetic wave, and it's fairly relevant. In general, this is true. It's a true thing for communication. You can. There are no effective ways of actually, so far, even though people have tried to actually transmit electromagnetic waves. No, I'm saying no. Transmit energy through electromagnetic waves in an effective way. For example, let's say I have an iron in one spot of the room, and I don't want to plug it into the wall, but I would like to have a receptor that will actually capture the electromagnetic waves and produce enough energy for me to actually run the iron over and iron a piece of cloth or whatever, okay? That has not been done very effectively, but the energy that you can, transmit through communications it's very important, okay? So people are working on effective way of transmitting energy. Okay, in that sense. This is more strange though. Electromagnetic waves also carry momentum. Okay, so it can be shown. I'm not going to go through the whole detail, but this here is the density of momentum in an electromagnetic wave. Okay, the density. I'm not going to go into the details now, but we will come back to this point later, because when we study the description of electromagnetic fields as quantum excitations, as photons, this will be certainly very evident the way we can produce these. Classically, it's not as easy to arrive to this expression, but let's leave it at this point. I want you guys to know that the density of momentum in an electromagnetic wave can be described by the modulus of the Poynting vector divided by c squared, okay? So the actual flux of momentum is the density of momentum, momentum on an electromagnetic wave and volume, and the same thing we did before, multiplied by the velocity it's traveling with, okay? So this is going to be C times dP divided by the volume, which will be that. So the flux will be S divided by C, okay? And, just rewriting the modulus of the Poynting vector in this way, we can find this expression, EB divided by mu naught C. So there are two real considerations that one must have to actually understand how this applies to anything, okay? Let's say we have two situations. We have an electromagnetic waves that actually hits a surface and is completely absorbed on it, okay? So it means that if this, you have to remember that what is the meaning of pressure? Pressure is something you have to do to let's say you have an ideal gas in terms of inside a container with one of the walls that can be moved. and you have to apply a pressure, a force to the to that movable wall that should be high enough to contain the gas inside. So if the pressure of the gas inside is increased, you actually have to increase the force on the movable part. And what is the meaning of the pressure? The pressure is essentially saying what you have to do is you have to, oops. Okay, what you have to do is actually change the momentum of the particle that collide with the inside of the wall. The same thing happens here. For example, this terms over here, the flux of momentum, if there is a flux of momentum that is totally absorbed, meaning you have this is the situation before and after it's totally absorbed, it means that the pressure you have to do for the absorption of that momentum is equal to the flux of momentum, is SAB over C. That is the pressure. If you actually calculate the units of this thing, it's essentially units of pressure, okay? But if the electromagnetic radiation is incident on a surface and actually is bouncing back because it's reflected, the change in momentum that the electromagnetic will have will be twice the flux that you will bring in. So in that case, the pressure for total reflection will be twice the actual value of the radiation pressure, okay? That is something you have to consider, and we have an example here, I think, that I took from the book. Yes, this is it, okay? So I'm gonna be reading this thing just to give you time to think about it. So we have an orbiting satellite that has a solar panel that collects energy with the total area of 4 square meters. So if the sun radiation, this is a satellite that it's in a near orbit around the Earth, okay? So the actual intensity of the sun is the intensity of the sun above the atmosphere, okay? And if it actually says here, if the sun's radiation perpendicular to the panel is completely absorbed, find the average solar power absorbed and the average radiation pressure force, okay? So there are two things here that one has to think. You have this S vector that is being produced by the radiation from the sun, and there's two things that will happen. These panels certainly are in a satellite are designed in general to actually capture the energy and transform it finally into electrical energy to move or do things inside the satellites, okay? But as this power, these electromagnetic waves, the light from the sun collides with the panels, would also produce a pressure, because we have a pressure density because everything is absorbed, okay? So if we go back here, we are in this first case, we have a flux of momentum, and then we have nothing, okay? Because all the energy is absorbed, okay? So let me go back here. So one should know, and probably this number is somehow mentioned in the book, that the power, the intensity of the sun in the upper atmosphere is 1.4 kilowatt per square meter. That is sort of a value. The typical value or the maximum value on the surface of Earth in a clear day is about 40% less. It's about 1 kilowatt per square meter, okay? So you have an idea of the number. So the total power that is absorbed is the flux of power, okay, by the area, because this is the flux times square meter, And now I have a finite area here, and the finite area of this thing, where does it say, is 4 square meters. So it's the modulus of the S vector times the area gives you 5.6 kilowatt for the total area, for the total power absorbed by the panel. That's a lot of power, actually. You know, if you have you know, if you run compared to a cell phone, for example, you know, this several, you can actually iron with this kind of power. Okay, that would be one of the applications, something like that. You get all the sun here, and you essentially, you need this sort of surface area, and then perfectly you can collect that, and you can, typically an iron has 2 kilowatts. So you can actually convert all this energy to electricity and iron. What I was saying before is that, you know, having something like this, like a focused beam of energy inside the house it could be dangerous, actually. But, you know, it's a mean of transporting energy. But here you can sort of go across this area, you're not going to get burned. Okay, so this is a good part. Okay, and then there is the pressure part. What is the force that you actually are exerting over the satellite? And the force, it's the radiation pressure, which is S, is this value, where is this value divided by C, okay? And that times the area, that gives a final number of roughly 2 times 10 to the 5 to the minus 5 newtons. Okay, so even though the pressure is really low, you can actually see an effect. It's in terms of force, this is going to be very slow acceleration that the actual radiation can produce for a satellite on Earth. Okay, but that is it could be a meaningful number if the object is actually very close to the sun, because this number can really increase, because this power is decreasing with the distance, like 1 over r squared. So if you get very close to the sun, you can get an important effect of the radiation pressure of the sun. And you can see that in general on comets that go very close to the sun, much closer than Mercury. The radiation pressure, meaning the effect of the radiation field from the sun on the surface of the comet, has something to do with the orientation of the tail that the comet has. Okay, so under certain extreme circumstances, something like radiation pressure could be something meaningful. Okay, there's a very nice experiment that I don't have the equipment to do here, but you should guys, if you come around the lab, you can actually hear the photons or the electromagnetic waves when they collide with a frying pan. Okay, if the intensity is high enough, you can actually do something like knock, and you can actually feel it when you actually activate a photo flash very close by to a frying pan. You can actually hear the noise it produces. That's a nice example. Okay, let's go to the next one. So this is sort of the general aspect of it. And that has to do with 2 quantities that you should keep in mind that an electromagnetic wave has. It has momentum, doesn't have a big impact at the level of the Earth, for example, and with the intensity of the sun. And the other one is they carry energy. Okay, the energy carried is much more important than the momentum for most of the applications. Okay, so we have actually not saying too much about the way the electromagnetic waves are generated, and we are not going to be describing that in detail in the course. We are actually looking at things when we are far apart